Hello and welcome to yet another lecture on basic electrical engineering. Myself, Prathita Roy, Assistant Professor of Sudhir, Chandra, Degree Engineering College, Electrical Engineering Department. So we have already discussed about the RLC series circuit. Now today we will concentrate on the RLC parallel circuit. So in order to find the RLC parallel circuit, this is the general construction of an RLC parallel circuit. Parallel circuit means the voltage will remain same and the current will divided into the three parts that we have seen. That is current is divided into the three parts, that is IR, IL and IC. So this is the parallel RLC circuit that we have drawn. So if the voltage is remain same, which is voltage will be taken as a reference. The parallel RLC circuit. So means the voltage will remain same, that is called the alternating voltage. We say A is the source voltage. And let us concentrate on the R, L and C that is connected in parallel. So this is R, this is L and this is C, and the current that is coming out from here, this is called the I, is divided into the three parts. From through the R, the current is going known as IR. So through L, that is current is flowing is known as IL, and through C, that the current is flowing is known as IC. So it is seen that the voltage will remain same and the current is divided into the three parts. So let us concentrate on the phasor diagram of an RLC series circuit. So it is seen that it will be done that we are taking the voltage as a reference. So the voltage will be taken as a reference, and the current through the resistance that is known to us as IR will be in the same phase with this voltage, that is the IR. So as we know that the current through the capacitor is leading with respect to the voltage. So capacitor voltage will lead it by an angle 90 degree with respect to the voltage. Capacitor voltage will lead by an angle 90 degree with respect to the voltage. It is leading by an angle 90 degree. Voltage is taken as a reference as because the voltage remains constant throughout the parallel connection. Voltage is same. Now in case of the IL, that is lagging the voltage by an angle called 90 degree. So we have to find the resultant current. So resultant current will be IL minus IC. Same process in order to draw the IC. In order to draw the IC, we have applied the same process. That is minus IC will be drawn from here. Same magnitude of this magnitude. So this is called the minus IC. So this up to that part, this is called the minus IC. And this part is known as IL minus IC. The process will be the same as we have done. So the resultant value will be this one, the current I, that is the vector, it is IL minus IC. So the resultant current, that is I, can be written as vector of IR plus IL minus IC. So this is a vector that IL minus IC plus IR. the resultant current IS here it is given. The current is IS. So resultant current is IS can be written as IL minus IC. IR plus IL minus IC. So what is the value of the IS? That is easily done. That IS square equal to IR square plus IL minus IS square. So we have done it. So the IS square can be written as IR square plus IL square, IL minus IC square. In that way, we can easily write the equation of IS. So IS, the magnitude of the IS can be found with the help of root over IR square. It is clearly that the IS is lagging the resultant current to the RLC parallel circuit is lagging by an angle, say theta phi. So this angle value can easily calculate. Phi will be tan inverse IL minus IC by IR. That easily can be done. Now let us, IS can be written as V by R, and where IL can be written as V by XL and IC can be written as V by X. So this is the total V by Z. So here the IS can be written as IR, means the voltage will be the VS. So we can write V by R whole square, and where the I of L can be written as V by XL. V by means we are taking the L into the form of, is converting from Henry or in Farad to the Ohm. It is V by X. So we can easily replace the XC values with the help of omega and L. So that is the total current, that is the IS equal to the IR plus IL plus IC, that I have given, that IS equal to minus V by R minus 1 by the integration of V dt minus A into dV equal to 0. So the IS equal to can be written as d2 V dt square plus dV dt of 1 by RC plus 1 by LC into V. So let us concentrate on the parallel connection of impedance of the parallel connection. So impedance can be written as Z equal to 1 by root over 1 by R square plus 1 by XL minus 1 by XL whole square. That is V equal to 1 by Z. So 1 by Z equal to, so it can be written as V by Z. So the 1 by Z can be written as, from that equation, 1 by R square. 1 by Z can be written as 1 by R 1 by root over of 1 by R square plus 1 by XL minus 1 by XL whole square. So 1 by Z can be written as root over 1 by R square plus 1 by XL minus 1 by XL whole square. So if you notice that the final equation of a parallel RLC procedure complex impedance for each parallel branch as elements becomes a reciprocal of impedance, and the reciprocal of impedance is known as the admittance. So first we have seen a new term called the admittance, which is generally known as reciprocal of impedance. It is generally known as admittance. So admittance Y equal to 1 by Z. This is called the reciprocal of impedance. So that is the admittance of a parallel circuit. Say all the impedance are known to us. So admittance is the summation of YT. Total admittance is the Y1 plus Y2 plus Y3 up to YN, where Y1 is 1 by Z1, 1 by Z2. It is given that 1 by ZT. It is a, and the admittance 1 by admittance, Siemens is generally known as the unit of the admittance. Okay. So all these are y1 plus y2 plus y3 is nothing but the 1 by z1 plus 1 by z2 plus 1 by z3 up to 1 by zn. And the unit is Siemens, and it is written as, or also abbreviated as a mho. The unit is also Siemens or the abbreviated as a mho. So admittance are added together in parallel bunches, where the impedance are added together in the series bunches. In case of the parallel bunches, the admittance are added together, and in case of the series bunches, the impedance are added together. But if we can have a reciprocal of impedance, we can also have a reciprocal of resistance and the reactance, as impedance consists of two components, that is R and X. Then the reciprocal of the resistance is called the conductance. That is, conductance is known as reciprocal of resistance, and the reciprocal of reactance is called the susceptance. So we are now concentrated on the conductance, admittance, and susceptance. The units of the conductance, admittance, and susceptance are the same as, namely known as Siemens, and which also can be through a reciprocal of ohm or ohm minus. But the symbol used for the each element is different. For the pure component as given as admittance, which is generally known as Y, it is given by the reciprocal of impedance is given by 1 by Z. So conductance, which is reciprocal of impedance, it is known as the conductance, is denoted by the G, and it is reciprocal of impedance. So all cases the unit is Siemens. Yes. So the conductance is defined as a E that with a resistor or set of resistors allow a current to flow through the voltage either AC or DC. Susceptance is generally the reciprocal of the pure inductance XL, which is known as susceptance. In AC circuit, susceptance is defined as a E that with the reactance, the set of reactances allow a alternating current to flow when a voltage or given frequency is applied. So susceptance can be written as in terms of BL or BC. Okay, so BL or BC means susceptance has a positive sign to reactance, so the so the capacitive susceptance BC is positive, and where the value of inductive susceptance BL is negative. So BL can be written as B angle of minus 90 degree, 0 minus JB, where BC equal to B angle of plus 90 degree, that is 0 plus JB. So susceptance can be written in terms of BC, that is 1 by XC, or in case of the B, that is 1 by BL, that is 1 by BL, that is 1 by XL, that is 1 by XL. So B generally the susceptance is known as 1 by X. So that the BL can be denoted as B, the magnitude of the B angle minus 90 degree, that is 0 minus JB, and where in case of the BC can be denoted as B angle plus 90 degree. So that is 0 plus JB. So this is given to us, and all the units are Siemens. So the impedance triangle can be written as resistance, reactance, and there is the impedance that we have done. And the admittance triangle can be written as, that is the admittance, that is the susceptance, and that is the conductance, G. So the admittance triangle can be written as, that is the G, that is the admittance Y, the conductance, and that is the susceptance, that is B. So the admittance triangle, and impedance triangle is known to us. So Y value is root over G square plus BL minus BC square. So putting the value BL equal to 1 by omega L and BC equal to 1 by omega C, the admittance is found that root over 1 by R square plus 1 by omega L minus omega C whole square. So Z equal to 1 by Y, it is 1 by root over 1 by r square plus 1 by omega L and so that's it whole square. And the power factors can be given that cos phi equal to g by y or phi equal to cos inverse g by y, tan phi equal to b by g, phi equal to tan inverse b by g. Same that we have done in case of the admittance and the impedance. Both are same. So y equal to g plus jp. So basically the y equal to g plus jp. So the magnitude of the y will be given. Magnitude of the y will be given as over g square plus b square, and the angle that is given equal to phi equal to tan inverse b by g. So the power factor cos phi can be written as b by y. Power factor can be written as g by y cos phi. Power factor can be written as g by y. Power factor can be written as that one cos phi equal to g by y. Power factor can be written as g by y. So let us take an example of parallel RLC circuit. They're given at 1 kilo ohm resistance, 142 milliamp Henry coil and 160 microfarad capacitor are all connected in the parallel across 240 volt 60 hertz supply. Calculate the impedance of the parallel circuit and current drawn from the supply. So we can easily find the XL equal to omega L 1 by 2 pi FL. Just putting those values, we just getting that it is frequency at the 60 hertz. So F is 60, 53.5. 53.54 ohm. Capacitive reactance X equal to 1 by omega C equal to 1 by 2 pi F C equal to 1 by 2 pi into 60 into 160 into the minus 6 equal to 16.58. So impedance can be found as Z equal to 1 by R by 1 by XL minus XC whole square. These are putting the value, we just getting the value of Z of 24.0. So supply current IS equal to PS by Z is 240 by 24, that is 10 ampere. Just putting these values, we just easily found the solution of a numerical problem. So let us concentrate another thing that is called the resonance. The resonance means if I concentrate on the resonance that is means the frequency at which the inductive reactance equal to the capacitive reactance means XL became XC. So the inductive reactance, the frequency at which the inductive reactance becomes the capacitive reactance is known as resonance. So XL means omega L. So XC means 1 by omega C. So it is found that omega square equal to 1 by LC. So from that particular equation, omega will be find 1 by root over LC. So omega can be written as 2 pi F equal to 1 by LC. So the frequency, the resonant frequency is generally known as FR can be written as resonance 1 by 2 pi 1 by 2 pi into 1 by root over LC in hertz. So this is called the equation of resonant frequency. The frequency at which the XL become XC means the resonant frequency. So at which the XM become XM means there is no XL and XC in the circuit. So only the impedance of the circuit at the resonant condition is the resistive. The circuit will behave as a purely resistive one during the condition of resonance. So it is seen that the circuit, both XL and XC, this part is omitted, so only the R is there in the circuit. So this is the resonant point. This is the frequency and the resonant. If I draw the graph between the frequency and the resonant, this is the frequency in hertz, and this is the Z value, ohms. The graph will be like that. The graph will be like this one, and this portion is known as Z equal to R. The frequency, this is generally dropped down a perpendicular line. This is called the resonant frequency or FR, and this is the general value. Top value will be given by value of R, that is given V by Z. V by Z will given the value of R, and this is the inductive part, and this is the capacitive part. So this is called the inductive part and the capacitive part. So this is the inductive, this is the capacitive. This dominant part is known as capacitive part. This dominant part is known as, the left hand side is known as inductive part. Okay. So we know that how we can draw it. We know that the XL, what is the relation between X value and the frequency? Let the XL equal to 2 pi FL. Okay. So means it is a straight line passing through the origin. That is the XL. It is the XL graph. And what is the XC? X equal to 1 by 2 pi FC. So that is the XC graph. That is the rectangle hyperbola. Because XL is 2 pi FL. So XL is directly proportional to the L that we have done, y equal to mx formula. So straight line passing through the origin, and x equal to 2 pi fc, 1 by 2 pi fc. So xc is proportional to 1 by, inverse proportional to 1 by f. So it is given that it's a rectangular hyperbola. So at this point, the frequency is known as, where the both values of xl and xc are same. This is called the, when the R is there, this is called the resonance frequency FR. So at that part, the capacitor is dominated. Here it is seen that the any value, say I drop down a perpendicular line, this value of the, which one is greater? It is the XL, that is XC, that is greater in that part. So that is written as XC greater than the XL in this part. So this part XC is dominating. So, and this part, for that particular part, which value is greater? For any instant, say that at that instant, if I draw a graph, perpendicular graph, we will see that the value of, at any instant, the value of XL is much better compared to XC. So in this part, XL is dominating as a XC. Okay. So it is a capacitive part, it's a inductive part, and that is given here. Now let us, we are concentrating on the bandwidth and the parallel resonance circuit. So what does mean the bandwidth? Bandwidth of a parallel resonance circuit is defined as the exactly the same way as the series resonance circuit. The upper and the lower cut off frequencies are given as F upper and F lower. Respectively denoted the half power frequencies of the power dissipated in the circuit is half of the field power dissipated at the resonant frequencies. It gives us the same as the minus 3 dB points, as the current value is equal to 77.7% of the maximum resonant value. So the bandwidth, if the resonant frequency remains constant and increase in the quality factor, will also cause decrease in bandwidth, and likewise decrease the quality factor will cause, and likewise a band decrease in quality factor will cause an increase in the bandwidth. And so the relation between the bandwidth is known as, if I see the bandwidth is generally known as, it is the F of upper frequency, it is the difference between the upper and the lower frequencies minus F of lower frequency. So the bandwidth can also be calculated in terms of quality factor of, so bandwidth can be written as resonant frequency by quality factor. So if I go through that quality factor, the sensitivity of the quality factor for a parallel resonance circuit is generally defined as the ratio of the circulating branch currents to the supply current, and it is given at quality factor is defined as a ratio of the circulating branch current to the supply current. It is given as R by 2 pi FL. R by 2 pi FL. It is known as quality factor, or in other words, we given as 2 pi FCR, 2 pi FCR, or same R by root over R into root over C by L. This is known as quality factor. So the bandwidth resonance can be given that the bandwidth is the upper, there is a lower frequency and the upper frequency, and distance between them is known as bandwidth. This is called the bandwidth. And there is a 3 dB decade, so it is value is 0.707, and it is a one value. So this is bandwidth is, and this is called the resonant frequency, and frequency that is the only the resistance is there in the circuit. So this is the difference between the two frequencies. That is the upper. This from this one to this one is upper. From this one to this one is the lower. So the resultant in the upper and lower is known as bandwidth. So this is called the bandwidth and corresponding quality factor. The relationship between the bandwidth and the quality factor known as the resonant frequency. So we have today learned about the RLC parallel circuit, corresponding bandwidth conception, quality factor conception, and the resonant frequency. The frequency at which the XL equal to XC, because the value of inductive reactance, there is no inductive reactance, there is no in, the value of inductive reactance is equal to the capacitive reactance. So means there is no X value in the system, no reactance in the system, only resistance are there in the system. Purely resistive circuit is known as bandwidth, and corresponding we are also see the conception of admittance and the impedance and the relationship. Thank you.